Hi everyone, I'm Dylan. I'm one of the instructors for Stat 231, and I will be running your tutorials this term. So I wanted to take a quick minute at the start of this video and introduce you to the face behind the Piazza name, and sort of try to help you guys get to know me a little bit better. So this term with the tutorials, I'm going to be trying something a little bit different. And my hope with them is to give you guys a somewhat entertaining way to supplement the material that's being covered in the Mobius lectures and in the course notes that are available on Learn. So each week what I'm going to do is join you guys in a video like this where I outline the sections that we're going to be covering this week. And so I'm going to divide each of these tutorial videos up into sections. Some of these sections will be reoccurring each week, and other ones might just be sort of one-off experiments. For your benefit, along with the tutorial announcement on Learn and in the YouTube description, which should be down there if you're watching on YouTube, then I will include timestamps so that you can jump around to the different sections in case some of it doesn't sound relevant to you, or if you're looking to come back to this at a later date. So in these tutorials, my hope is to cover sort of both the laundry list of items that you should have been learning over the past week. So in this case, it's going to be from weeks 1 and 2 because we haven't had a tutorial yet, but otherwise I'll sort of summarize the important concepts of the last week. And then I'll look at an example problem that tries to put all of those concepts into play as best as I can. And then from there, what I want to do is explore some of the ideas and some of the concepts in this course in sort of a deeper way, in a way that might give you an appreciation for the concepts outside of Stat 231 directly, that might sort of help you better understand some of these concepts in more detail, or that might help you in your life beyond Stat 231. So I'm really interested to hear any feedback you have. If there's anything that's working particularly well or not working at all, definitely reach out to me and let me know. I'm always open to hearing questions or comments from you all. This is a really challenging semester to be a part of, and anything that I can be doing to help your e-learning experience, I'm happy to do. So please do not hesitate to reach out. So with that, I'll actually sort of formally start the first tutorial. And so in this tutorial, part 1, this introduction, so congratulations for making it this far. In part 2, what I want to do is take a look at the key takeaways from weeks 1 and 2 in this course. So I'll just go over what were the concepts that you should have pulled out from the course notes or the lectures. In part 3, I'm going to take a look at an example problem. And so this example problem is using some data that my cats actually helped me generate. And so I'm sure at that point I'll figure out a way to post some pictures or videos of them in that portion of the video. Part 4, I'm calling Thinking Statistically, and so what I'm doing in that section of the video is exploring a concept, in this case the correlation coefficient, and I'm exploring it sort of more deeply to try to help you guys get a better intuitive sense of what it is, but also show you how you can interrogate statistical ideas to come to a better understanding of them. In the 5th part of the video, I'm going to be looking at outside of Stat 231, and so what I mean by that is we're going to take a look at the mean and the median as measures of central tendency, and in particular I'm going to approach it from the perspective of a data science interview. And then in the final part I'll actually just come back here and wrap up the video and let you guys know sort of what the focus is for the next week of this course, and make sure that we're all on track before tutorial number 3. In this tutorial, our focus is on the material from weeks 1 and 2 in the course, where there was quite a lot covered. Most of the concepts that have been covered will be used extensively throughout the remainder of the course. As a result, it's important that you understand what each of the concepts refers to, and that you will feel comfortable with them coming up in the future as assumed knowledge. I'd like to re-emphasize that the tutorial is not designed to replace the lectures or the course notes, but to supplement them and to make sure you're taking away the right lesson. To begin, you should understand what is meant by populations, processes, samples, and units. The entire point of statistics, as far as we're concerned, is to use samples to make statements regarding the larger population or processes at play. If asked, you should be able to identify, for instance, what the sample or population are with respect to any particular example. Next, you should feel comfortable hearing about variates, which represent characteristics of a unit, and attributes, which are functions of the variates. In particular, you should feel comfortable differentiating between the types of variates, so that's continuous, discrete, categorical, ordinal, and complex, and on their role in a particular setting, so whether they are explanatory or response variates. The types of methods we will be able to use depend on the types of variates that we are working with, and correspondingly, it's important to be able to properly identify them. Next, we discuss the types of empirical studies, namely survey samples, observational studies, or experiments. Given a particular study, you should be able to comment on what type of study it was and defend why you say it was that type. The bulk of the content discussed both numerical and graphical summaries of the data. You should be comfortable computing and interpreting the numerical values. So for instance, what does a kurtosis of 5 tell us, or a skewness of -2? For the bivariate summaries, remember that a correlation coefficient is only appropriate when the variates are continuous or ordinal, and a relative risk is for categorical variates. So that might include discrete ordinal, depending on the setting as well. For graphical summaries, you should feel comfortable knowing when a particular type of chart is appropriate, know what information can be read off of each chart, and whether this information is sometimes, always, or never available, and be able to actually read that information off of the charts. The empirical CDF was presented both in a mathematical definition and as a graphical summary. The empirical CDF is a powerful tool, and for a continuous variate, they actually tell us everything that we could want to know about our sample. Finally, you were reminded of some of the statistical distributions that you learned in Stat 230, which you should review. You should feel comfortable with these distributions, and in particular, you should review their respective features, so the mean, variance, distribution functions, and so on. You should also have R up and running on your computer. While you'll not be expected to write R code from scratch this term, having a statistical computing language handy will make your life much easier, particularly on the timed assessments. I would advise heavily to start getting comfortable running code that has been provided, and I would advise to do that as soon as you can. My 2 cats, Charles and Sadie, have this wonderful habit of jumping up on my desk to prevent me from getting any work done. So by the way, if I'm ever a little slow to reply to your emails, you can probably assume that my cats are standing in the way, and I will get to you as soon as they choose to move. Now, the fact they do this is wonderful for 2 reasons. First, I get to take pictures and videos of them frequently throughout my day, which is wonderful. And second, it allows me to generate data to use as example problems in Stat 231. So every time that one of my cats jumped on my desk, I recorded a number of pieces of information about it. I wrote down which cat it was, which is either Charles or Sadie. I wrote down how many hours it had been since they were last fed. So the way I did this was I just counted the number of full hours since they were fed the morning before. So that's an integer number somewhere between 0 and 12. And I also wrote down how long they stayed up on the desk for, which I've rounded to the nearest second just to make things easy. I recorded the first 100 observations that occurred, and the data should be available on the course website as cat_visits.csv. Using this data, we want to explore some of the concepts that have been covered so far. To begin, let's consider the following 7 questions. Basically, we just want to play around with summarizing these data and see what we find. The first 2 questions we can answer without needing to look at the code at all. So this study is probably best described as an observational study. Let's consider why. First, could we reasonably describe this as an experiment? A key feature of an experiment is that the individual running the study should be intervening in some way, updating a treatment variable of some sort, and then seeing what happens. If instead of letting the cats jump onto my desk on their own accord, I pick them up and I place them there, just to see how each of them reacts, then this could have been an experiment. But since it's simply a natural process that I'm observing, it's likely not best described as one. Now, with a sample survey, we're typically intentionally selecting a representative sample of the population and collecting data on those units. If, for instance, I was interested in the pet behavior across all people involved in Stat 231, so both the students and the instructors' pets, perhaps I could have sent out a request to some random selection of you to provide information about your pets. This would have been a sample survey. Now, as an aside, if you ever do actually want to share information or pictures of your pets with me, please do so. Like, seriously, it will always be making my day. But back to the question at hand, because the observing of my 2 cats is not a representative sample from any meaningful population, it's not likely best described as a sample survey. So as a result, we conclude that it must be an observational study. For the second question, let's consider the 3 variates separately. So first we have cat name. This is either the value Charles or Sadie, and as a result, it is best described as a categorical variable. Often during analysis, working with categorical variables directly is less preferable than working with categorical variables encoded as discrete variables. In order to do this in this data set, I've added a column that encodes Charles as a 0 and Sadie as a 1. This is a discrete and, in particular, binary variate. We do not describe this as ordinal, since there's no particular ordering of the data. In contrast, we can look at the hour since fed variable and note that this is ordered data. In particular, a 0 means that they were fed this hour, a 1 means that they were fed last hour, and so on. As a result, this is an ordinal variate. To complement this variable, I've also added an additional variable called 6 or more, which is a binary variate that takes a 1 if the hours since fed variable is larger than or equal to a 6, and it takes a 0 otherwise. Finally, we look at the visit length variate. This is measuring the time of a visit, which we typically describe as a continuous variate, because at least in theory, time passes continuously. Now, it's sometimes tempting to take a variate like the one presented, since it's rounded to the nearest second, and describe it as discrete, since we are counting the number of seconds. There may be cases where this is appropriate. The general rule of thumb, however, is to ignore the tool that you've used to measure. So just because we only could record to the nearest second does not mean that with a better tool, we may have been better able to discern the continuous value. As is usually the case in statistics, there are no hard rules for this, so it's best to use your judgment and, when in doubt, to justify your answer. So it's worth noting the key difference between the visit length variate and the time since fed variate is that the former is measuring a duration of time, while the latter is measuring a count of intervals of time. I could have measured time since fed as a unit of time instead, which would have made it continuous. However, it's measuring the number of complete hours that have passed since, which is a discrete quantity. I included these 2 variates to demonstrate the importance of considering the intention of a variate for describing its type, but also just to show that these definitions need to be flexible. Next, we begin to look at the summary information for the visit length variable. First, we have to load the data into RStudio. So if you're not sure how to do this, take a look at the module posted on Mobius. Once the data are loaded, let's also make sure that we have a skewness and kurtosis functions defined. These were given in the assignment 1 folder and will need to be run once per session. For the mean, it's a pretty simple call. We can just use mean and then pass in the vector that we wish to find the mean of. In this case, that is the visit length property of cat visits, which we type in as cat visits $visit length. Doing so, we can see that the mean is 95.18. On average, my cat stayed on my desk for 95.18 seconds after arriving. The median is similar, where we have 2 different ways of computing it easily. The first is to use the median function in exactly the same way as the mean. Alternatively, and this was shown in the Mobius content, we can use the 5num function to get the 5-number summary. This contains the median as the 3rd item. Both of these methods return a value of 97, so that means that half of the times my cat stayed on my desk for less than 97 seconds, and the other half of the time it was for more than 97 seconds. The last measure of location that was introduced in the course notes was the mode. Now, generally speaking, the sample mode is a less useful measure of central tendency than either the sample mean or the sample median. This will not always be the case, of course, but very often the mode will not return a useful measurement. This is emphasized in R by noting that there is no way built in to compute the mode in a single line. My recommendation instead would be to plot a histogram of the data and consider looking at the maximal bin rather than the mode, specifically when you have a continuous covariate. In this case, since the data were rounded to the nearest second, we can plot a histogram that has a bin size of 1, which shows us how many times each number came up in our sample. From the histogram, we can read off that both 108 and 118 are modes of this data. If instead we had used a bin size of 20, we see that 100 to 120 serves as the modal bin, which also happens to contain both of our actual modes. If you have samples of a continuous variate, you would never expect to have a unique mode in your sample. In fact, in a sample of continuous variates, you would expect that every value you observe is observed only once. As a fun exercise, try to think about why this is the case. It's related to how we talk about the probabilities of continuous random variables. So, as a result of this, the mode becomes a far more useful measure when we're dealing with discrete or categorical data. We could consider the mode of our cat name variable. Here we see that 0 is very clearly the mode, meaning that Charles jumped up on my desk far more than Sadie did. Next, we consider the measures of variability in the data. In particular, we compute the variance, standard deviation, range, and interquartile range. The variance and standard deviation are both computed using a single command. So we can get the sample standard deviation using the SD command, and if we square this value, that leaves us with the sample variance. We see that the sample standard deviation is approximately 22.24, and the sample variance is 494.6. The range and IQR can both be obtained using the 5-number summary we previously computed. The range will be the 5th element minus the 1st, and the IQR will be the 4th element minus the 2nd. This gives us a range of 123 and an IQR of 29. That means that the longest time my cat stayed on my desk was 123 seconds longer than the shortest time that they stayed on the desk. The IQR says that the middle 50% of the visits were within a range of 29 seconds. Finally, we can look at measures of shape. Both the skewness and the kurtosis are calculable using functions given in the assignment 1 file. Making sure that we have run these in advance, we can simply call skewness on the data and then kurtosis on the data. Doing so results in a skewness of negative 0.319 and a kurtosis of 3.21. This means that we have a slight negative skew to the data. The left tail will be longer than the right tail, since our sample skewness is negative. The kurtosis is slightly larger than 3, which means that there are more tail observations in the data than we would expect if we were normally distributed. The 5-number summary asked for in question 4 was already computed for the previous values. So we can output the 5-num variable and see that our minimum was 31, our first quartile was 81, the median is 97, the third quartile is 110, and we observed a maximum value of 154. So by way of numerical summaries, we've looked at just about everything. Now it's time to consider some graphical summaries. We've seen a histogram which showed us the general pattern of the data, but let's take a look at another one. The general results we saw in the numerical summary, a slight negative skew, heavier tails, and so on, are all visible in this plot. Whenever we have a continuous variate, box plots also tend to be useful for investigating the data. Looking at the box plot by itself essentially gives us a similar value to the 5-number summary. More interesting, however, is looking at a breakdown of box plots by which cat we're considering. Using the formula visit length squiggly line cat name, or visit length as explained by cat name, and passing the cat visits data frame in as a data parameter, we get the 2 box plots side by side. Here we can make some interesting observations. First, Charles stayed longer than Sadie did. In fact, the lower quartile for Charles is roughly the same as the upper quartile for Sadie. This seems to make sense with my experience. Sadie tends to regret her decision to jump up almost immediately. It also appears that the variance of observations for Charles is smaller than the variance of Sadie's visits. Again, this makes sense to me. Sometimes Sadie really enjoys being up here, and sometimes she really does not. Charles, on the other hand, tends to mostly be okay with it, no matter what. We could also use hour since fed as a grouping variable. We have to be careful interpreting these box plots, since each box could potentially have very few observations, so there's 13 boxes and only 100 observations total. Still, looking at this box plot shows a very clear trend. As it has been longer since I fed them, the longer they're willing to stay. Again, this makes sense to me. They know their dinner time very well and always make sure that I do not forget it. One last chart to consider is the empirical CDF. Creating it is as easy as passing the eCDF function into the plot function, and doing so with some graphical adjustments will output this plot. A good exercise is to take a look at the eCDF plot here and see if you can come to the same conclusions regarding the data as we saw with the numerical summaries. So for a continuous variate, the eCDF tells us everything that we could want to know about our sample. And so we should be able to read off all of the information. Of course, actually reading off specific values from a chart can be difficult, so in practice, the table of the eCDF would tell us everything that we wish to know, but still. So for instance, we can try to grab the median value by tracing a line from 0.5 over to the chart. In R, an effective way of doing this is to call the AB line function once you have the chart generated. So if you call AB line and you pass a parameter h, this will draw a horizontal line at the value that's indicated. So in our case, AB line h equals 0.5 marks a horizontal line at 0.5 to indicate our median. Now I like to pass the LTY or line type argument and give it a number of 2 or 3 so that it makes the line non-solid. Now you can also pass a parameter v, which draws a vertical line at the indicated value. So our median was 97, so AB line v equals 97 will mark this on the chart. We can see that this is the level that's indicated by the median line. I'd suggest playing around with the chart some more and see if you can pick out the other quantiles, the minimum and the maximum, and if you can figure out the approximate skewness, so whether it's negative or positively skewed, from the eCDF directly. Of course, if you have any questions at all, please reach out to me. In terms of summarizing visit length, those are probably the most appropriate charts, though there's always the possibility for different selections to display interesting information. A run chart's not appropriate since our data are not observed sequentially over time, and scatter plots require 2 continuous variates normally. Still, there may be some flexibility in how you choose to display the information. The next question is, does the length of stay appear to be exponentially distributed? We might think that the length of stay should be exponentially distributed, since we often use the exponential distribution as a measure of time. Think back to Stat 230, where you likely used it as a distribution that light bulbs go out according to, for instance. There are quite a few ways to assess this question, both numerically and graphically, so let's consider a few. In an exponential distribution, both the mean and the standard deviation are given by theta. In our sample, we observed a mean of 95.18 and a standard deviation of 22.23, which is quite different. That begins to suggest that the exponential distribution may not be appropriate. In an exponential distribution, the mean is expected to be larger than the median. Our mean is 95, which is less than our median, again, giving evidence against this exponential distribution. Exponential distributions also exhibit positive skew. Our skewness was negative. So far, this is definitely not looking good for the exponential distribution. We can also consider some graphical displays. So I'll leave the histogram with the density function overlaid as an exercise, largely because if you remember the density of an exponential, our histogram is far from it. Instead, let's consider the empirical CDF with the theoretical CDF plotted on top. Doing so, first we make sure to expand the x limits to include 0 with the plot, but then overlaying the values, we see a terrible fit. This, along with the numerical evidence above, suggests that there is no indication that these data are exponentially distributed. I wanted to compare 2 exponentials since, before considering the data, it may have appeared to be a reasonable model. However, giving our data a look at all suggests that it's nowhere close. This underscores a key difference between statistics and probability work. In probability, you assume a model and parameters, and then assess the likelihood of events under that assumed model. In statistics, you observe events, and then you try to find a model and parameters which would make your observations likely. The final question involves bivariate summaries of the data. The 2 that have been discussed so far are the sample correlation and the relative risk. Sample correlation is appropriate only between two variates which are both continuous or perhaps ordinal. We could, as a result, consider the correlation between the visit length and hours since fed, since there's an explicit ordering in both of these variates. Calling the core function produces a result of 0.845. This is a strong positive correlation. This means that there's a positive linear relationship between how many hours have passed since I last fed the cats and how long they stay on my desk. The relative risk is appropriate between two discrete, categorical, or ordinal variates, and it's generally used to determine whether factors are statistically independent. In theory, then, we could check any of the cat name or hours since fed variables. So to showcase, we'll use the cat name bin and the 6 or more factors, and compute the relative risk between these factors. We can use the table function in R to generate a frequency table. Calling this, we can see the output, which indicates that 25 times Sadie jumped up on my desk when it had been 5 or less hours since they had last been fed, and 5 times she jumped up when it had been 6 hours or more. Similarly, Charles jumped up on my desk 63 times when it had been 5 or fewer hours since they had last been fed, and 7 times he jumped up when 6 or more hours had passed. Using this, we can compute the relative risk for jumping up when it had been fewer than 6 hours as 25 divided by 25 plus 63 all over 5 divided by 5 plus 7. So this gives us a value of 0.68. We interpret this to mean that Sadie was 0.68 times as likely to jump up when it had been fewer than 6 hours since she had last been fed than Charles was. We could also compute the relative risk when it had been more than 6 hours as 63 divided by 25 plus 63 over 7 divided by 5 plus 7. This is 1.23. This means that she has a probability that is 1.3 times higher to jump up when it had been 6 or more hours than Charles does. Whether we think these values are significant enough to deem the cat name 6 or more variables to be independent is a judgment call that we can make. I'm inclined to believe that Sadie is more food motivated than Charles, and so perhaps that makes some sense. In any event, I encourage you to play around with these data, to get comfortable with the concepts in the first 2 weeks, and to be more comfortable playing around with R. The next section of the tutorial will consider further questions related to sample correlation. My idea with the Thinking Statistically section of a tutorial is to more deeply explain a concept in the course to try to help develop an intuition for looking at a problem statistically. A lot of statistics and probability is unintuitive, and part of being a good statistician is fighting against our gut instincts when looking at a statistical claim, and falling back on our experience and knowledge to interrogate how our instincts may be misleading us. For discussion today, I'd like to dive into the sample correlation, and consider how the intricacies of a statistical definition are important. We define the sample correlation mathematically to be the ratio of the sample covariance over the product of sampled standard deviations. This obscures its real meaning, and so often we use the following to describe it. The sample correlation, which takes values between -1 and +1, is a measure of the linear relationship between the two variates x and y. If the value of r is close to +1, then we say that there is a strong positive linear relationship between the two variates, while if the value of r is close to -1, then we say that there is a strong negative linear relationship between the two variates. If the value of r is close to 0, then we say that there is no linear relationship between the two variates. With that in mind, consider the following multiple choice question. There's a random quantity y, which is known to be related to a random quantity x. Moreover, we know that if the value of x is large, then the value of y will also be large, and if the value of x is close to 0, then the value of y is also close to 0. Which of the following is true? A, the correlation between x and y is positive. B, the correlation between x and y is approximately 0. C, the correlation between x and y is negative. Or D, none of the above. Give the question some thought, and we'll come back to it in a moment. The key point in this definition is that it is a measure of a linear relationship. It's important not to translate linear relationship into relationship more broadly. This can seem like a minor quibble in the definition, but it's really the difference between answering the above question correctly and not. And it's the difference between developing a strong intuition for where correlation is appropriate and where it may not be. The way the question is worded, there's an intentional push to have you think that A is the correct response. And indeed, in many datasets where the relationship is as described, this will be the case. So in this dataset, there is in fact a strong positive relationship, and A would be correct. Indeed, the relationship here has a correlation around 0.98. But remember, when creating one example where something is true, that's certainly not enough to conclude that the statement will always be true. So is it possible that the other statements are true as well? Consider the option B for one moment. Is it possible that a dataset where high x means high y and near zero x means near zero y also exhibits no linear relationship between x and y? What about if the graph looked something like this? In this quadratic relationship, we see that whenever x is high, y is high, and whenever x is around 0, y is also around 0. However, there's basically no correlation between x and y. The correlation is about 0.04. Another way to consider this case is that if we were to draw the best straight line to fit this data, the line would, 1, fit the data very poorly, since a linear relationship is entirely inappropriate, and 2, would be basically horizontal. What this means for us practically is that when the relationship in the data is nonlinear, we do not expect that there will be an informative correlation with the data. The correlation here is almost 0, but this does not mean that there is almost no relationship. It just means that the relationship that does exist is far from linear. Now, is it possible for statement C to be correct? And, as you've probably guessed, the answer is yes, but for one example, consider the following. These data might look like slightly more of a stretch, but we see that they do technically fit the description. So when x is large, the values of y are the largest that they take on, and when x is near 0, so too are the y values. However, it's very clear that the linear trend tends to be negative across most of the data, and indeed the correlation is negative 0.35. As a result, the answer to the previously asked question must be D, that none of the above are guaranteed to be true. The point regarding correlation is important in its own regard. There are many times where correlations are used inappropriately. We'll discuss this more in Chapter 8 when we tackle the fact that correlation does not imply causation, which just so happens to be everyone's favorite statistical saying. It's important to reflect on the fact that a correlation is a measure of the linear association between two variables, and nothing more. However, this point is also important to take more broadly in this course. When you read a definition, pay particular attention to all of the details provided. The clarifying words that may seem unimportant are included for a reason, so make sure you read through them carefully, investigate each definition to probe your intuition, and, if in any doubt, please ask questions. It's quite likely that many of you might have some interest in pursuing a career in data science, or perhaps a co-op. It's a great option for students studying statistics, and many of the concepts that we talk about in this course will be fundamental to the work that a data scientist does. Today, I'd like to offer a brief piece of advice framed through the lens of a data science interview. So imagine you're in an interview scenario, and you're asked the question, why is the median a better measure of central tendency than the mean? Now, the answer that they're looking for revolves around the fact that the median is more robust to extreme outliers than the mean is. Consider, for example, the distribution of incomes. Most people earn incomes that fall in a range of, say, $0 to $75,000. However, there are a few individuals who earn a lot more than this, say $250,000 plus. While there are fewer of these individuals, the extreme discrepancy in the values of their income has the effect of pulling the mean higher, perhaps dramatically so. The median, on the other hand, will always sit at the point where half of the population earns less and half of the population earns more. This forces it closer to what most people would intuitively view as the center of the data. This type of question could be framed in a number of different ways in an interview setting. So for instance, you could be presented with some data that have extreme outliers, and you're asked to explain why the mean is such a strange value. In any event, it's quite common to hear the refrain that the median is better than the mean. This leads many people to the conclusion that using the mean is a bad thing. When confronted with the fact that we often use means in statistics, this can cause some confusion. The point I'd like to make today, generally, is that there are very few statistical absolutes. There are very few statements we could make that are true in all situations, always. And the statement that the median is better than the mean is certainly a statement which can be false. Now, there's a few reasons why. The first, most obvious, and least interesting is that if our data are symmetric, then the mean and the median are the same point. It's only with heavily skewed data, like incomes, that there becomes a dramatic difference between our mean and our median values. The skewness is important here, rather than just the presence of outliers. If outliers are equally likely to be large or small, so that the distribution is still symmetric, then the mean and the median will still coincide. A more interesting reason comes from the fact that, depending on your data, the median may actually distort more than the mean. Consider grades in a semester for two separate students. What would happen if we summarize the students based on median? We would see that student A had a median grade of 68 and student B has a median grade of 91. That means we are concluding that, based on the medians, student A is a B- student while student B is an A+ student. This is despite the fact that these students actually did fairly similarly. Student A performed better in 4 of the 5 courses, but in the course that they performed worse in, it was quite substantial. What if we looked at the means instead? Both student A and student B had a mean grade of 80. This seems to do a better job reflecting the true state of their grades. I will leave you to think of one other point where the mean may actually be preferable to the median. So imagine a scenario where I record the number of minutes of sunlight per day over the course of a month, and I give you the choice. I can tell you the mean value, or I can tell you the median value. Either way, I'm being very rude, and I'm not going to let you see the rest of the data. From your perspective, you're interested in the number of minutes of sunlight before noon in the sample. Is there a strong reason why you would prefer one over the other? Certainly give this a thought, and definitely let me know what you come up with. Okay, so welcome back. Right now I just want to talk quickly about what's going to be coming up for the next week of this course. So over the next week, we're basically going to be covering maximum likelihood estimators. So the idea here is to provide a flexible framework for estimating the parameters of a statistical distribution given some observed data. And so maximum likelihood really sort of lays the foundation for a lot of what we do in statistics. It gives you sort of a very solid base for working from, and it's an incredibly important concept. Also, for those of you who are more mathematically inclined, it's certainly more mathematical than what we did in weeks 1 and 2, so there's that to look forward to as well. Now, when you're going through these notes, I really would like it if you focus on what we're meaning by likelihood specifically, so trying to develop sort of your intuition about what the likelihood's referring to, and then from there, sort of understanding what that's saying about these estimators that we're developing. So they're the maximum likelihood estimators, and the process itself is sort of routine, but I think understanding what the likelihood refers to specifically and how we go about using that is a very important lesson to take away from this next week. And then next week when we're back here in tutorial for week 3, I'll definitely sort of dig into those concepts a little bit more and make sure that everyone is sort of completely understanding what it is that was being covered. So with that, I'm going to end the tutorial here, but I just wanted to give you one final reminder that if there was anything in this video that worked or didn't work, please reach out to me and let me know. If you have thoughts or feedback or whatever else, I'm always happy to hear it. And if you just have questions about the course content more broadly, feel free to reach out to me. I hope that seeing me here in my closet is a way to make it feel a little bit more approachable to reach out to me and ask whatever questions you might have. So hope you enjoy the next week of your course, and I will see you back here on Friday for tutorial from week 3.